It's the square root of gm over r, where m of r is the mass inside the orbit of the star. Now the orbital speed theta, capital theta, can be converted to an angular velocity. Remember, theta, capital theta is the linear velocity. So let's define omega as the angular velocity, little omega. And then omega of r is capital theta of r over r. Little omega is simply then capital theta over r. And both omega and capital theta are functions of the radius. Now, at the sun's location, we can define what the angular velocity is. Capital theta naught is 220 kilometers per second, and r naught is 8 kiloparsecs. Therefore, for the sun, you can define an omega naught, which is theta naught over r naught, which is then equal to 220 kilometers per second over 8 kiloparsecs. That gives you then about 30 kilometers per second per kiloparsec. If you want, you can cancel the kilometer and the kiloparsec, and this will become 0.028 radians per million year, 5.8 times 10 to the minus 3 arc second per year. So let's see what we expect to find. We know the Keplerian rotation is going to have the linear velocity falling as the inverse of the square root of the radius, the angular velocity falling as the radius to the power minus 3/2. If you have constant orbital speed, which is a fairly good approximation for most of the Milky Way, you have theta capital is constant. That means that the mass is proportional to the radius, and omega falls as r to the minus 1. And then, for the sake of comparison, we also have rigid body rotation, where omega is constant, and therefore it's capital theta that's proportional to the radius. You can convert this to how mass is proportional to the radius, and for the Keplerian case, the mass is constant. For the constant orbital speed, the mass is proportional to the radius, and for the rigid body, the mass is proportional to r to the cube. So if the disk of our galaxy was in rigid body rotation, then stars would have the same orbital period regardless of distance from the galactic center. However, the disk is actually in differential rotation, with omega decreasing with radius. We expect stars closer to the galactic center to be passing us, while stars farther from the galactic center fall behind. So let's now construct the analysis of the galaxy's differential rotation that was performed by Jan Oort in the 1920s. As I said before, this is a simple exercise in trigonometry, following this diagram here. So how can we determine the velocity theta of a random star in the galaxy, knowing the observations d and l, the distance and the galactic longitude of the star? Knowing also the velocity that the sun is going around the galaxy and the distance from the center of the galaxy to the sun. Well, one thing we can determine from observations of the star is the radial velocity. It's a spectroscopical measurement. Can you find it in the radial velocity of the star relative to the local standard of rest? Now, from the Oort diagram, then, we can define that there's this angle alpha. And then the radial velocity is going to be the velocity projected along the line of sight. Have then that the radial velocity, let's call it VR, is equal to capital theta times the cosine of alpha. And removing from that, then the radial velocity of the sun itself along the line of sight, which would be theta naught times then the cosine of this angle here, which is 90 minus L. So that becomes capital theta cosine alpha minus capital theta naught sine L. Now, alpha is the angle between the star's velocity vector, which is this, and the line from the star to the sun. This is an angle that we cannot measure. So we must eliminate alpha from this equation by using trigonometry. How do you do that? So the line from the sun to the star, which is this line here, and the line from the star to the galactic center, which is this line, they define a triangle whose vertex angle equal L at the sun, 90 plus alpha at the star. And you can see that from realizing that the angle from the galactic center to the star with the vector, with the velocity vector, is a right angle, 90. So if this angle is alpha, this angle here must be 90 minus alpha. And if this angle then is 180, if this is 90 minus alpha, then this must be 90 plus alpha. And then to complete the 180, then this angle here must be 90 minus alpha minus L at the galactic center. Now we can apply the law of sines for this triangle. Let's copy this to the next page. Again, what we are calculating is what is theta, capital theta as a function of distance. And we must find a way to eliminate alpha from this equation since we cannot measure it. Everything else we can measure. We can measure the radial velocity, we can measure theta, nod, we can measure L, but we cannot measure alpha or theta, so we must eliminate alpha. So if we apply the law of sines for this triangle, then we have the sine L over R, L here, and this is the radius. It's equal to, then we can apply for here, for this angle and for this side, is equal to sine of 90 plus alpha over R nod. And thus we find an equation for cosine alpha. If we substitute that in the equation for the radial velocity, then we find that the radial velocity is equal to R naught times the sine of the galactic longitude times capital theta over R minus capital theta naught over R. And this is the definition of the angular velocity, right? Remember, angular velocity is capital theta over R. So you can substitute this and then find a simple expression for the radial velocity. Vr is equal to omega minus omega naught times R naught sine L. So this is known as first Oort equation. This permits you to compute omega in terms of the observables, which are the radial velocity and the galactic longitude, and the known values for omega naught and R naught. And as you can see, if you have constant angular velocity, this factor here cancels, and then you indeed have zero radial velocity, as you expect in radial rotation.